almost. We're live now.
All right. Hey, everybody. So if you joined us last week, my name's Kevin, and I'm here with my friend Zach. We're going to do some live coding. If you didn't join us last week, this is a fun little about an hour for us to dive into some problems, see how someone who's a bit of a beginner to the Wolfram language would solve a lot of typical computer science type of problems. This is indeed the live coding with Kevin and Zach stream. I think we're having a bit of an issue with the name of the live stream on Twitch. So if you're following us on Twitch, this isn't Q&A with kids. This is live coding with Kevin and Zach. Um, as some of you know, I just finished my junior year at Boston University, and I'm an intern at Wolfram Research this summer. And I'm here with my friend Zach,
Hello, I'm also an intern at Wolfram
University,
Research. My
and I'm
background
an
is all in
intern at
physics.
Wolfram
I do a
Research
lot of
this summer.
experimental physics, and I'm currently trying to get a master's in physics. My research is at the CMS experiment right now. No experience really with Mathematica and the Wolfram language, so excited to hop in.
Yeah, with that, let's just go ahead and start solving some problems, see what we can do. So what we've got right here is we created a way to go into this Rosetta Code website, which is a really great website where people can host questions for computer science type of problems. And as we can see here, there's a curated list of a lot of different problems that have yet to be solved with Mathematica, the Wolfram language. So what we want to do is just start solving them. We're going to grab a random one of these and we're going to try to find a good solution to it. And then hopefully we can help improve this website by adding some solutions. So the code right here is just going to create a big list. You'll see it pop up when it's done of these are all the URLs of problems that have yet to be solved in the Wolfram language. What we want to do is get a random one of those. I stored it in a variable called links. So if we apply the random choice function to links, we get one of those random links. We can see, okay, we can get different ones each time we run this. And let's just use a quick system open function. Oops, system open. Spell open, that is, will open up a random link in my web browser. So pretty easy to do that type of web scraping and then using a variety of services through the Wolfram language. All right, it looks like the problem that it gave us is something called list rooted trees. And it looks like there's some lore. We have came back from grocery shopping. We put away all the goods, but we're left with a pile of plastic bags, which we want to save for later use. We're going to take one bag and stuff all the others into it. Okay, so we've got a bag of bags, and we're throwing it under the sink. Okay, this problem's fun. So, we realize that there are various ways to nest the bags, with all the bags viewed as identical. Interesting. If we use a matching pair of parentheses to represent a bag, the ways are, okay, if there's one bag, you've got a bag. If there's two bags, you've got a bag inside of a bag. But then it gets interesting. With three bags, you can have a bag inside of a bag, which is inside of a bag, or you could have two bags inside of a bag. So it looks like they're representing bags as parentheses such that anything inside of a set of parentheses is the bags inside of it, and any open closed pair is a single bag. So for four
Okay,
bags, there's this set.
so
This
I
looks fun, right, Zach?
this is interesting. Although, to boil it down, this is just a game of like probability. It's like how many different ways can we put bags inside of bags inside of bags?
Mm-hmm. Yeah,
So,
it's a sort of a permutation type of thing, right?
yeah.
In fact, I think I've seen a similar problem before, and this is just how you represent Catalan's number, which is a recursively defined series. I'm gonna see what Wolfram Alpha has to say about Catalan's number, or maybe Catalan's series. Let's see. So right here, I've pulled up a Wolfram Alpha query. We get that by just typing in two equal signs into a new cell. and then we're able to search Wolfram Alpha, which is an online database curated by Wolfram Research, and it'll give us pretty much everything that it knows about this. So this is something. Let's see. So for n equals 1, it says that there's one bag. For n equals 2, it says there's 2. Okay, so maybe I'm wrong. Maybe this isn't what I was thinking of. Let's start off by thinking, what do they want us to do? That's the real question.
So we can do like they want like us to make, I guess, an n-rooted tree. I don't even know what that means, to be honest. But each root of the tree represents, you know, an arrangement of bags. And it looks like we have I think that OES number indicates to a numerical series. I don't know if you want to follow that. I
Yeah,
might look it up.
yeah, so OEIS is the Online Encyclopedia of Integer Sequences, which is pretty neat. It gives you any sort of integer sequence like this. This is the number of unlabeled rooted trees with n nodes. So I think the difference here between the problem that I was thinking of is that they say here all the bags are identical. So in fact, having something where you've got a bag inside of each other on the left side is the same as having the bag inside of each other on the right side. So they don't want you to reiterate that, it looks like. Yeah, they've only got it here on the left and not on the right.
Okay.
Now I wonder how can we get this sequence in the
I'm pretty sure we
Wolfram
can just pull
language?
up numerical sequences, right?
Right. I'm gonna again go to Wolfram Alpha for that.
Oh,
Yeah, it looks like it's got the right sequence there.
that's cool.
Um, yes. Okay, cool. And we could even get this as some computable data. So there we've got the list. If we wanted more, we could get that as well. How does it? Okay. This would be more interesting. So this will tell us we can at least know how many we should be getting. So that's good. That's a good way to check our work. But it looks like they want us to actually be printing out these parentheses or any
Okay.
tree representation. Oh,
So how can we represent this as a tree? I don't know. I know there's a lot of stuff with like multi-way and step-way graphs, and don't really entirely understand what they're used for,
right.
but they are fun visualizations. So can we maybe try one of those? I'm not sure.
Yeah, I'm gonna open up some documentation here. And I know there's been a lot of added functionality with representing trees in the Wolfram language. So yeah, they say trees here in the title. I believe what they're referring to is, at least this is how you would represent a tree in Mathematica. A branches off into B and C. Or if you can nest trees, you've got a tree where A branches into a tree where B branches into C and D, but A also branches into E. That's pretty neat. Now I guess you could represent nested bags this way. What do you think?
I mean, it could work. I'm not entirely sure how to apply it. So
Yeah,
definitely, any some testing could be used.
right.
Yeah.
Well, it looks like so there's always got to be one external bag, right? The bag that all the other bags are inside of. So that could be the head, this A,
Hmm.
and then say you had another bag B that can only go inside of A.
Hmm.
But if you had three bags, you could have A, then B, and then C, where C is inside of B, like this first one. Or you could have A with B and C inside of it, like this. So
Hmm.
I think the way we represent that is, so this is an example of three bags. We're labeling the bags A, B, C. You've got the branch where it's tree of A, B, C, and you've got the branch where it's tree of A, tree of B, C. Hmm, let's
Seems right. We could try to make our
this one too. So I need to put all these inside of lists. I should have read the documentation properly. Yeah, so this is kind of similar to this representation here. So you've got the option where
3 bags nested,
three
and
bags
then 2
nested,
bags
two bags
inside
inside.
the third.
Yeah.
So inside C would be 2 bags.
Right.
Okay. All right.
Now, how do we scale that up to n bags? Maybe if we did something with subsets where we can get, so you've got a list of A, B, C, you can get all the subsets of that list.
I think this might be, yeah, this might be the right way to go.
Yeah. Let's think about it, because how would we represent this? We've got the tree. What about? So I'm looking down here at the C also. So I know that subsets is something similar to what I probably want to use, but in C also it's going to give me related functions, and hopefully maybe one of these is actually what I wanted.
Okay.
Oh, look at that. So this constructs all binary expression trees with 4 leaves. Interesting. One of the great things about the Wolfram language and about Mathematica is that you can write code right inside of the documentation. So we've got a documentation page here, and I can just write my own code right below it, see if it works. I can copy the documentation example. Pretty handy. And then it looks like they put this in tree form. Interesting. So this was with 3 bags, and I did get 3, but this doesn't look like the structure that we expected. This looks pretty different from what we saw before. What's actually going on here?
Is there an absolute limit to how many bags? So there are like rules though, right? We could start by, coming up with some rules, right?
Right.
So I guess I'm not entirely sure.
And also, I just want to point out, if anyone that's watching this has any suggestions or thinks we're missing something, feel free to post something in the chat. We'll be happy to try your example. We're always happy to have the audience help us get unstuck.
So I don't know. Looking at non-overlapping circles. I'm just reading the online encyclopedia of integer sequences a little bit. So it's also, we can also look at this as a power sequence. So, for 4 bags, there are 4 different arrangements of power sequences.
How so? How do you get the 4?
Well, I'll just sort of show. So I'll put this in the Zoom chat so you can look at it. But if each bag corresponds to an X, so there's 4 identical X's.
Right.
These are the 4 distinct, groupings we could have.
So correspond. It's this guy. Okay.
Yeah.
Oh. So this is, you wrote this right here, but you used X instead of parentheses, basically?
Yes, that's what it was. I mean, the bag way makes sense if we were holding bags, but I look at that and I'm like, that is a lot of parentheses.
All right.
So definitely see where we're going.
Yeah, so what we're doing here is just, it looks like every single one of these has 4 X's. Every single one has 3 carets between the X's. And all we're doing is moving these parentheses, right?
Yes. Yeah, that's it. And while you work on that, just for anyone joining us, we just like technical difficulty. This is not the Science and Tech Q&A for kids. This is live coding with Kevin and Zach. Just a bit of an error. If you're coming in, you are more than welcome to listen and stay. But if you came on a misunderstanding, that's okay too. Hope you have a good day.
I hope we're
Um,
fun, but not exactly Steven, I understand.
it's okay. So yeah, so like this is a way of looking at it. This is the parentheses problem, but with, we have a term here and we have like less of a, you know, less of just parentheses.
Right.
So if this might help kind of put an understanding of what's going on. So as we increase, so if we go back to the top and look at our number sequences,
The sequencer.
with no bags, there's no combinations. With one bag, there's one combination. With one bag, two bags, there's one possible combination. That's x to the x power.
Bag inside of a bag.
With three, there are three different permutations, which I guess is x to the x, and then like x to the x. Like the other bag is being, you swap out one of the bags as your power sequence.
Right. Yeah, because it has to do with moving these parentheses inside of each other.
Yeah. Yes. This is n equals 4. So that's why there's 4.
Oops. Clean my notebook a little. Always nice to keep a neat little notebook, so I've added a chapter title.
So yeah. So that's
Right.
kind of like what we're looking at. So I guess, there's obviously got to be a really fun way to visualize this in like the language in Mathematica.
Yeah, I want to use this tree functionality.
Brian, someone from the Twitch chat, Brian says that we could just recursively build it. And you are right, we could recursively build it. But we're kind of fishing for like, I guess, a more clever way to do it and kind of explore like what we could do, because I'm vaguely aware there are really clever ways of visualizing this and like building this. And we also don't want to, you know, light our processor on fire trying to build this to like, the 10th amount, because it looks like we have 235,000 permutations at some point, which is gonna be a lot.
Yeah. And it
So
looks like they only want us to go up to maybe 5 bags. So hopefully we won't have to yeah, get those big numbers. We can see the series grows very quickly.
I didn't even think of that. Okay.
Yeah, so each time there's a bag outside, and then we start opening and closing bags inside. So you always start with one bag outside. We could basically ignore that, I guess, because you always have the external bag wrapping everything, right? Then on the
Yes.
inside, you start opening and then closing, and then opening again, and then closing.
I just sent you a general enumeration that someone is, giving us as a way to kind of visualize this. Not too sure how to do it. You might have a bit more of an idea. This is from IDUD. I'm sorry
Yeah,
if I
what are
just butchered that.
these?
So yeah, we're just looking to get the number of solutions and print them, but we'd also like to, look at it and like visualize it, because hopefully we should be able to.
Right. And do it using some of the built-in functionality
Oh,
that should make it pretty
this is
easy.
pretty clever. Okay, all right. Someone actually just
You got
gave
a new
us
idea?
the bag. No, this is from someone. This is from SG
Ooh,
Huseman. Thank you. This is
looks
pretty
like someone
speedy.
has written out some code.
We do just want the number solutions, and but we'd also like to
Ooh,
print out our bag, because it would be kind of cool to, see what a bag looks like. I think
ooh.
this is for N-5, if I'm guessing, but I might be wrong on that one. It looks like there's 20.
I think the difference here is that in the problem, they only want solutions where all the bags are inside of a single bag. So it looks like these,
So
this one,
the closing ones that close like outside, so the leftmost column where they close outside of other bags, that's not a good solution, because they all need to be inside of one of the bags.
right. Yeah, so, okay.
So
Yeah,
like
this
that's the
one,
point where
there's
we
a
have
bag
a failure.
outside.
Yeah.
Yeah, but we're getting close, and I
So
like
we have a messy sink.
I like what's going on. Let's try to break this down here. So, oh wow, we're using fixed point. replacing strings. Wow, somebody put a lot of effort into this. Kudos
Yeah,
to you.
this is from one of our past Innovator Award winners, so
Great.
has to be expected. This is really good. I mean, we wouldn't have thought of it. So, thank you very much.
Yeah.
um,
So
yeah.
we're
So
selecting from
yeah.
this guy. So this is going to be even bigger, probably. Yeah.
So this is just well, this is just a column. So we're replacing any time where it closes. Theoretically, any time where there's a closed parentheses, it gets rid of it.
Hmm.
So somewhere along the line, these bottom ones are like not being removed, even though they should be removed.
I see. I wonder if, what if we just did what was done here for one less and then wrapped it in parentheses to put all those bags inside of a bag? Um, and I see that, okay, this is actually where this note comes in. So because all the bags are identical, the strings where you've got bag inside a bag on the left and bag inside a bag on the right are the same configuration, right? If we if we're looking at it this way and we just spun ourselves around this way, we'd be seeing this guy over here. So since we can just change how we look at it and see the same thing, these are identical in terms of how the problem's set up. So what that means for us is that these two solutions right there are also identical. So we'd somehow need to be able to get rid of those identical solutions.
These are
Um,
identical. Now, would they also be failures because they're not inside a bag? I guess. Oh, well, we're assuming
oh,
this is all inside a bag, though, right? We're assuming everything
yeah.
is inside a bag.
Yeah, my idea was to just have, um, just wrap all this inside of, that's actually not gonna work. So I'm just gonna put some open bracket and closed bracket around this guy. Maybe that'll work. And I'm using infix join notation, I believe, which is kind of ooh.
Well, we made a lot. We made a real
we made
output there.
we made a lot. What I'm going for here, oh maybe those are supposed to be two tildes, is so I'm gonna head over to the documentation again, and there's a way where you can fix strings together. Okay. That's when you're
Fixed point
looking
stuff is
for
needed to
this.
verify. Oh, I see. Okay, so SG
Hmm?
Usman just he wanted to chime in a bit. We were looking at our the fixed point.
Oh,
That's
good.
to fix invalid double parentheses inside of each other.
Mm.
So there's gonna be errant like invalid combinations. I'm not really sure, entirely sure. I'm sorry. Some of
So
the math, some of
this.
the math series stuff kind of goes over my head, so I get a little confused. Stuff like that is probably what we're looking at. That's like where we
Yeah,
have issues.
because
So,
if we look at it for every closing parentheses, there has to
mhm,
be an open parentheses that comes
yeah,
before it, which is why
yep,
solutions like this aren't valid.
I
Um,
see.
but the
Okay.
reason why those are coming up is because we're in this code, we're just taking all of the permutations
Hmm.
of this constant array. Oh, and here's that join type of. So just for people who aren't really familiar with this type of how it's written out, what we've got is join squashed between two things that we want to join. And when we use those tildes, it tells us to apply join to both of them. So for example, I could do it with some function f, where this is going to squash the 2 and the 4 into the function f. This is mostly helpful with functions like join, where you want to join something on the left. So say I wanted to say hi to Kevin, I could join hi to Kevin, and oh, it, if I had used the right join, this would have put them together. But join is for lists, so I would need to use string join, of course. Yep. So we join the two strings hi with the string Kevin, and we got hi Kevin using this
So
notation there.
so if we try to put your your parenthesis you added in a list, would that work? Would that make that string join or that integer join, or I'm sorry, the iterative join?
Yeah, let's what I want to do before I mess with it is just see what it looks like. So we know how to change it. What
Okay.
yeah, well, what I had been doing was trying to change something that I didn't really know what it was in the first place. Not always a great idea. Um, what we really want to do is take every single one of these and wrap it
A parenthesis.
in parentheses. Yeah.
So
So
so we could just should we add just a string join front and back? Would that work? I have no idea.
yeah, I think maybe what you're saying is because I think we can pass more than 2 arguments to string join.
Hmm.
Yeah, it looks like we can. We can do any number. Um,
Okay. So we can use this the double with this. Oh,
is what you're saying?
I that's that's exactly I think what I wanted. Let's compare. Put the bottom one, the cell below. I'm sorry, the cell below in column representation too, so we can compare.
I think I want to do it here. So yeah, just to catch everyone up, what I did here is I basically this is a new function that I created, and what this function does is it joins something. This represents the input to the function. It joins that string with an open parenthesis and a closed parenthesis. And so when we map it, this is the map operator across those previous results, we
What's
get
the
those
ampersand
results.
operator?
So the ampersand closes off our function.
Oh, okay.
And this hashtag or pound symbol is the slot in Mathematica. And what slot does, maybe if I can, ooh, what slot tells us is there should be an input here.
Ah, okay.
So if we define a function where it's 3 plus slot, close it with the ampersand, then when we apply that to x, we get 3 plus x.
Mhm.
So the input to the function goes into the slot.
Okay.
Kind of cool. And so then when we map that across our previous results, we get those results wrapped inside of parentheses.
Okay.
Yeah,
All right.
so we're in a really good track here, thanks to this helpful comment from people online. What we need to do is get rid of duplicate solutions like this.
So, let's look at this and say, how many bags are there right now?
Mm.
Square brackets, hacky way with the square. Okay. We may try that SWSH. Let's in the meantime, how many permutations or how many bags are we looking at right now?
I think
I
we've
would
got
guess
4
4.
bags. Yeah, we've got 1, 2, 3, 4 bags inside of each other.
So,
And we can see that because it's n plus 1. So 3 plus 1.
just as a test, I just try this. Take the two identical inputs
Right.
and pass them through a triple equal sign comparison. I'm just curious if they're gonna be like considered the same,
Huh.
if the
Um,
language would just consider them that way.
yeah, let's see. So what I'm going to do is, oh, that was a little messy. I'm going to grab them one at a time. So we want to compare, well, what we want to compare them is, I mean, obviously this string isn't the same as this string, right?
Yeah, it's not exactly the same, but I know that there's the double and the triple equal that will kind of like mediate these kinds of things. So I don't really know. I'm not
What
sure if we
we're
could.
what we're looking for is if they're the same under permutations of closed bags, which is kind of tough,
What was the
right?
permutations? Never mind. I'm actually not sure.
Yeah, so what we're
Um,
saying is if we took this and permuted it such that we move this bag over to the left, now
yeah.
it's the same bag, right?
So could we try the permutations function?
Yeah, let's see.
I was messing with that a little earlier and I didn't really get much usable, but it seems like it could work.
There's a lot of things that we can do with permutations.
We could try the I think in the permutation operations,
Mhm.
there's a permutations and then a permutations replace. So
Permutation
we might want to
replace.
use these kinds of things for it, because this
Right,
might be what we're looking for. I mean, let's try to see if we can produce, if we take the permutations like function,
right.
can we try to produce that other output?
Mm. Yeah, and what I'm gonna do instead is try it on, let's see. I want to try it on an in list form. I feel like it would be easier to permute
Yeah.
in list form, but what we really want to is to group them by open and closed, right? Because we don't just want to move one bracket. We only want to move groups of bags, and a bag is a closed bracket, right? We've got one
Yeah.
bag, and then we've got a bag inside of a bag.
So we
Um,
just want to, how do we test that, I guess is what, I guess
yeah,
I get what you're saying.
how do we move bags without moving a
Together,
bag through another bag, right? Because if we were to
violating
move
some
this bag, it
laws.
would have to go through a bag.
We'd have to take it out of our bag.
Mhm.
We'd have to clean our kitchen sink, and that is unfathomable at this time. So, you know, we're gonna have to figure out how to move, I guess, identify closed bags.
Yeah. And this brings me back to that tree form that we looked at a little bit before.
Hmm.
Um, I really want to get
I
that to
think that would be
work.
a cool way to see it. Yeah, I feel like that'd be a
Yeah.
really cool way to visualize it. They talk a lot about trees. Sometimes Steven will do them in his blogs, and like they're all around.
Oh, cool. Um,
I don't know.
yeah, how are we gonna make these trees? It's probably back here to groupings, and I feel like there's a way with groupings.
Mm.
Um, maybe what if I'm gonna try this groupings function that they have here and try to show it in as a tree graph, and we'll just see what it looks like.
So,
Um,
so if what does the 4 and the 2 mean in this?
right. It looks like it's 4 leaves to the tree
Mm.
and two. It's taken two at a time.
Okay.
So it's all the possible groupings of range of 1 to n, where in this case n was 4, and we're taking them k at a time, so two at a time. I'm not sure. I wonder why two. What I don't really like is that this tree form includes the list, which is the head. I wonder if there's a
Well, we can.
feel like we can say so list is the head of any list, just like plus is the head of addition. Power
Mhm.
is the head of exponentiation.
Well, so
Um,
we did kind of come to, or we're looking at the indices of integer sequences, the
okay.
encyclopedia of it. We do. This is like a power relation. So,
hmm
you know, I guess if that makes sense. I don't really. It's very
Yeah, but how are we going to
confusing.
create that sequence?
Yeah, I'm not entirely sure. And that's why, like, I think in the meantime, we can stick to just doing the list. And then once we kind of figure this out and we kind of figure out the list stuff, then we can, like, okay, how can we transfer this to our really nice, fun way of visualizing stuff, tree form and stuff like that.
hmm
So we can kind of, at least for the meantime, like, take that. I'll
True.
look
Try to
into
get it
some
in some
stuff.
way.
Yeah.
I'm gonna try something. So it looks like to get it in a tree graph, it needs to be. So we need it in a form where we've got something pointing to something else. And my idea was to get rid of the list groupings and instead replace those with rule groupings, so that one would point to 2. I don't think that worked here. I don't think that worked here because I ended up replacing the whole list instead of just part of it. What are you seeing, Zach? Anything that looks good?
Right now I'm just kind of I'm looking at some of the built-in ways that Wolfram like can take a list, produce some, some functionality based on it, like recurrence relations and things like that.
Mm-hmm.
I would say, the permutations that we got from SG Huseman, very helpful. I think that's going to be our best way to go for at least in the meantime. At least if we can't do anything else, we can at least visualize it. And we can also just take the length of these columns and we would get, the number of options.
Right, for sure.
So we don't have to show them, but we can at least like just get the length of them. So I think if we can figure out how to relate these two identical ones, that would make sense for n equals 3. Actually, this is 4. So this would make sense. There would be 4 possible combinations because there's n minus 1 permutations.
Right.
That makes sense. I think. Yes, I think so. Someone will correct me if I'm wrong.
Yeah, I'm wondering if maybe since we know that bags have to open and then close, right? You can't close a bag before you've opened it. What if there's a way that we can represent bags as just being an object, right? So we've got this external, or let me look at a more interesting example. We've got this external bag, which is holding another bag, maybe we'll call that bag B, and another bag C, which is holding bag D. For example, we could write that as A is holding B and also C, which is holding D. Something like that. And maybe that can be written as a tree graph. 2U. Oh, it doesn't look like that's a good graph. That's definitely not what I was expecting.
That's fun. It's a fun way. I liked it though.
Yeah, if it looked like how I expected, it would definitely be very fun. Maybe I'm doing something wrong. Is this the same operator that I'm using? Oh no. What is that? All right, so now we've got a question of what the heck is this symbol? Because I was assuming that it was the same as the rule, but it is in fact not, as it is a directed edge.
Oh, well, that makes sense.
Interesting. So maybe I need to replace these with that directed edge symbol. Does that make any more sense? No, I don't think so.
It's a nice arrow. I'll give you
Very
that.
nice arrow. Thank you. If you needed a way to create an arrow in a very obfuscated way, this is it. I think in the Wolfram language we could have just said arrow. Oh, maybe not. We need to specify something about that. Let's see. Oh, it needs to point from point 1 to point 2, so 1 to 2. Oh, 2D points, of course. So, the origin. This is completely unrelated to what we're doing, but if you wanted an arrow, you can make it in a way like this. There's an arrow. So this was just a very complicated way to create that arrow.
I will run that. Someone just sent some code in, so I will run this code and see what it does because I'm actually kind of curious about it.
Cool, you want to send it my way? We'll
yes,
see.
I will send it to you.
It's pretty long.
It's a recurrence relation, so it's gonna take some time to run,
Okay.
but it'll give us the answer. I'm all right, that's all I'm really looking for.
All right,
But
so yeah, let's see
mm,
what's going on here. Um,
let me send you. Do you need to put in the first instance? That's gonna be important.
yeah, okay. So with a recurrence relationship, you're going to need to define the base case. So we've got here the base case of when f is applied to just one, it's just a single closed bag. Um, Otherwise, it is, I'm not sure what's going on here.
Well, let's, it's running it, I think. Oh, wait. Yeah, that's weird. I don't actually know if that's how it.
Did it
I
work on
think
your computer?
no, it didn't work. I think I know what it's supposed to do, but we'll see in a second if I'm right.
Uh,
It's f of. I think you need to remove that f of n.
hmm.
I think it just needs to be like straight to one. Oh, oh, sorry about that.
Oh, what's going on?
Well, this is leaving us stumped.
Yeah, we are.
I feel like I'm learning more about integer sequences. I think last week we dealt with another um like integer sequence from oh, I don't actually know what's going on then. We dealt with another integer sequence from from a previous problem, and I feel like I'm learning more. I didn't even know there was an encyclopedia of integer sequences, so
Right?
very cool.
Yeah, and all that can be queried using Wolfram Alpha, which is always helpful.
So it's a pure function.
Yeah, I think there must have been an issue with me copying this over, so I'm just trying to maybe rewrite it. Okay, yeah, so there was an issue with me copying this
Oh,
code.
okay.
Sometimes happens. Let's just see. It looks like
Oh,
we're getting
so 2 is
closer.
1, 3 is 2, which is right. F of 4, there are F of, or I'm sorry, 4 corresponds to 4, options.
Beautiful.
It looks like it removes that, what's it called? If you want to display as a column, that would be kind of cool to see. It looks like it also removes that extra one that we didn't have. It's fun
Yeah,
to see that it's inversed to what the Rosetta code solution was.
you're right. That's a good point. Yeah, so let's look at what's going on here. So like I said, this is a recursive relationship. So we've defined a base case. When the input is 1 to this function f, we are left with just a single bag. And then for greater n, this means anytime you see n in what follows, replace it with the input to the function f. This is the delayed assignment operator, which means that this function won't be defined until you actually run f. All that's, the minutia. But what's really going on here is we've got a table where we join. This is similar to what I wrote up there, where we're wrapping something inside of parentheses. So we're putting some list of bags inside of another bag by joining these strings. Okay, that's cool. And we're doing it for um, x is going up to the integer partitions of n minus 1. And that's the list of all possible ways to partition the integer n into smaller integers. Oh,
That's
neat.
cool.
Okay. Yeah, okay, so it's like all of these lists sum up to 5, right? We've got 5, 4 plus 1, 3 plus 2, 3 plus 1 plus 1, 2 plus 2 plus 1, etc. Okay, very neat. So it's all the possible ways to sum integers to get that integer. And then
Yeah,
we
memorizing my device.
do it for all of those. And we do it for all y's, which are in
Oh, I get
this.
it. Okay, so I guess from the code that we were given, the
Hmm.
reason that there's that extra f of n is from what I understand, it's memorizing. I think it's explained for someone in the chat. It's
Memoizing?
memorizing each previous f of n so that when it computes it, instead of computing, however many, it computes less. I don't know if we're just like compiling it wrong, which is completely possible. Um, but that's kind of like the reason behind it. So,
Oh, oops, my bad.
well, that's cool
Let's
to see the
figure
character code.
it out. Yeah. Oh, okay. Ah, I see.
That's
Okay,
very
so what
cool.
they're
Thank
saying,
you
I
for
actually did
explanation.
not know this. This is really neat. So when you've got something defined recursively, right?
I'll send you what he said so you can kind of like you can read it and not get it from me.
Mm-hmm.
Yeah, so I pretty cool. I didn't know that.
Yeah, so when you're doing a recursive function, if
You
you're calling it for the 100th value, that function's also going to call the 99th and the 98th and the 97th, and it's going to have to compute every single one of those fresh when you run it. But what this is saying is, okay, instead of doing that, if we've already ran f of 3 and we know that, then just store that as f of 3. And then when we run f of 5, which needs to call f of 4, we already know what f of 3 is, which is called by f of 4, so we don't have to compute that again. So this is basically just saving us a lot of time through something called memoization, which is basically loading results that you've already done so that you don't have to do them again, pretty much.
Okay.
That's really neat. So that's a big time saver there. And it makes the recursive a much more convincing argument as to why you should do that.
Okay. Cool.
Something that is also new to me in here is this function called outer, and it looks like when you've got some list of f, or sorry, you've got some function f and you do it to lists, and what it does is it takes f and applies it to each of those lists. Wow. The generalized outer product of the list, forming all possible combinations of the lower level elements in each of them and feeding them as arguments to f. That's pretty neat. So as you can see here, we've got f of a and the first one over there, a and the second one, a and the third one, then b in the first. Wow, that's really neat. And
Okay.
wow, this is great. Okay, we've got a list of those, and they're prepending the list to it. Okay. Interesting. Yeah, so this is a really neat solution that we got from someone online. And what this goes to show is that there's a lot of ways to do something. This is the recursive way to do it. If we wanted to actually get the final answer, which is what this looks like for 5 bags. Great, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9 of those bags, which is the correct answer. There should be 9 ways. And we've got a bunch of bags inside of bags here. And this was a way that some people in the chat definitely wanted to do, which was recursively. So using the definition of the function f, or using the function f inside of its own definition, that generally tells you it's a recursive function. And this was a really clever way to do it. I think this utilizes the Wolfram language pretty strongly because it's got a lot of the great built-in functions like integer partitions, which you didn't have to rewrite them. You can just say, hey, what are all the ways that we can sum up to 5 using integers? Oh, great, there's a function for that. So yeah, there's a lot of really cool functionality going on here. I hope maybe we were able to explain a little bit of what's going on in there.
Even if not
Thanks.
explain, explore.
Explore, yes. Explore what's going on in here. We are
uh,
computational explorers
so
diving into the world of computation. And yeah, thanks for everyone who gave some suggestions, some actual working code. I can tell you worked pretty hard on that, so that's great.
really great involvement. I really appreciate it. This is what it's all about. We're two pretty novice. Kevin's been coding longer in Mathematica than I have, but we're both pretty, not in the loop when it comes to a lot of these time-saving measures and these, interesting ways to implement Mathematica and the Wolfram language. So we are very appreciative of it.
Right. Yeah, this was great. Thanks for showing up, everyone. And I think with that, I'll just say we'll give it a wrap and have a great week, everybody.
Have a great week.